Great, Steve, thank you. Thank you all for coming and for tuning in to watch this. I'm a geologist, and I know fully well that you are never supposed to call soil dirt. This is partly why I called my book Dirt. Why? Well, I'm not that good at following directions, first of all. And secondly, if you look at what has happened to soils worldwide over the course of the agricultural era, the last 7, 8, 9, 10,000 years or so, we have turned an awful lot of soil into dirt. We've moved it off of productive agricultural fields and put it places where it was not so productive. Thus the title. But I'll make no apologies for the title, despite having been taught explicitly in soil science class to never ever call soil dirt. But why would a geologist like myself spend the time to actually write a whole book about the way that people treated land and how that has affected societies in the past? It's because in studying erosional processes, the processes that shape topography, because I'm the kind of geologist that's known as a geomorphologist. I study the shaping and sculpting of topography. And you can't get away from the processes of erosion and the movement of sediment around the landscape. And over the course of my career, I've come to actually realize that soil is a strategic resource. It's every bit as much a strategic resource as the things that we tend to think of. Oil on a geopolitical basis, water, as we heard the other day in terms of future, the atmosphere in terms of what's happening to the climate. Soil is essentially the global environmental crisis that's happening slowly enough that we don't tend to talk about it or focus on it to the level that it actually deserves in terms of its status and magnitude as quite literally sort of a quiet global crisis. So if we think of soil as a strategic resource and we look at the pattern of soil degradation in the world today, and taking a map from the UN, there's an awful lot of regions of the world where agricultural soils have been degraded to one degree or another. And you'll notice there's an awful lot of red and orange areas on that map, areas where soil has been degraded or very degraded. And there's some areas where the soils are not so degraded. But one thing I want to point out at the start of this talk is, although I'll be talking a lot about soil degradation as a global problem, you could look at any of those red areas on that map and find individual farms or even a number of farms where farmers are intensively working the land to produce food, but actually improving the quality of the soil. So this kind of a map, this kind of global analysis, a lot of what I'll be talking about is painting with a fairly broad brush, and by the end of the talk, what I want to get to are some promising developments in terms of the way we can actually turn around the long-term degradation of soils that is, as I'll be talking about, characterized many societies throughout history. So if we look at what the magnitude of the soil degradation problem really is, David Pimental and colleagues a while back now wrote in a review that over the past 40 years, which writing in the 1990s, that meant in the post-World War II era, soil erosion caused the degradation of some 430 million hectares of land worldwide. That's an area that's about the size of India and China combined, about 1/3 of all present cropland. That's land that we've degraded the agricultural potential for. If you think about the problem of feeding the world 50 or 100 years out, it would sure be useful to have all the potentially available farmland in the world at full productive capacity. We've already degraded a lot of it. It can, I think, in the end be reversed and undone, but it could take a while, and it will definitely take focused energy and changed policies. But how big a problem is this in terms of rates? At the same time, they were estimating that the estimated world rate of soil erosion was on the order of 23 billion tons a year or so. That's a net loss of under 1%, about 0.5% to 1% a year of soil and cropland that is being degraded. Now, to most people, a rate of less than 1% a year is pretty small. That's not a terribly big annual return on anything or loss of anything. But thinking like a geologist, if you just take that number of 0.75% or so and play that out over time, it only takes about 150 years or so to project out that we'd be literally running out of topsoil off the world's croplands. And if you take the high end of the estimates, it would be even sooner. Now, I'm not going to argue to you today that I think that the world is going to run out of soil. But what I will argue to you today is that the pace at which we've been degrading agricultural soils over the last several centuries is quite transparently not sustainable. And what I think that means is that agriculture is going to change over the next century. It will need to change as the human population keeps rising. We simply cannot afford to continue degrading farmland. We're going to have to figure out how to farm intensively while building and maintaining soil fertility at the same time. And I think we could do that. Now, if we think about the problem of maintaining a civilization over the long run, there's really no mystery to the idea that some of the key controls in the longevity of human societies are things like climate changes, natural disasters, politics, wars, social evolution, the kind of things that we would read in history textbooks. Now, if you look at the climate change issue in terms of societies in the past, there are droughts in antiquity that took out dynasties in ancient Egypt. There was the cold snap of the Little Ice Age that did in the Viking colony in Greenland. There's absolutely no controversy over whether climate changes in the past have influenced the longevity of human societies. In terms of natural disasters, well, similarly, there's no real controversy that natural disasters can affect human societies. If you look at the Greek island of Santorini and the Bronze Age civilization that was there, they lived in an active volcano, kind of like I've got Mount St. Helens up there on the screen in my home state of Washington to illustrate volcanoes. That's not Santorini. But what is it about natural disasters and volcanoes in particular in this example that could influence the longevity of a society? Well, back to the island of Santorini, they built on an active volcano. Why would they do that? They had geothermally plumbed hot water in the Bronze Age. It was one of the most advanced civilizations in the Mediterranean at their time, but they had absolutely terrible land use planning. They built on an active volcano. When their homeland erupted out from under them, it was game over for their island kingdom. Now, if you think about the influence of natural disasters on societies, though, there's sort of a scale dependence to them. A small island state on a single volcano is very vulnerable to disruption when that volcano erupts. A large dispersed global society can, at least in principle, take aid from one area that's unaffected by natural disasters and bring it to areas that are affected. And so there's a scale dependence to the dependence of natural disasters, unless, of course, something like the event that took out the dinosaurs 65 million years ago is repeated at a global scale and Bruce Willis is unavailable to save the world. In terms of politics, wars, and social evolution, I mean, that's the stuff you see in history textbooks, right? I mean, you crack open an environmental history textbook or any textbook, and those are the things that really make the stuff of history. And I'm not arguing that those things don't matter. Clearly they do to the course and fate of human societies. But the question that I want to ask, that I wrestled with in writing this book, was the question of what about the soil? We know that the fundamental condition for maintaining an agricultural civilization is sustaining the soil itself as a physical body on the landscape and the fertility of that soil. Something like 90+% of our food comes directly or indirectly from the soil. Most major civilizations have been agricultural civilizations, and we know that that is a factor. How big a factor was that in the history of human societies? That's the question that I grappled with in trying to write this book. And given the title of it, I've probably already given away my opinion about it. But I want to walk you through some of the examples and a little bit of the data, some of the history, and how we might actually turn the long-term problem of soil erosion and degradation around. Now, if you look in environmental history textbooks in particular, you'll find the argument that soil erosion from deforestation helps to explain the demise of civilizations around the world. All those societies over on the right-hand side of the screen are places where that argument has been made. But as a geologist who's worked on erosional processes in upland environments, in mountain regions and hilly regions, regions that are prone to erode rapidly upon deforestation, I noticed some other things that kind of complicate the argument that you tend to find in environmental history textbooks. And that is, quite frankly, that trees grow back fairly rapidly. I've worked in coastal Oregon now where there's been several cycles of timber harvesting over the last 100 years, and we've been able to document greatly increased rates of landsliding, but off of very small areas of the landscape. The numbers simply don't pencil out in terms of a broad region to look at the pace at which you could explain the wholesale loss of the soil over large regions. And this started me to wonder whether it wasn't simply a question of deforestation as the driver behind the erosion that has that imperiled many civilizations, but whether it was the agriculture that followed, whether it was the plow and not the axe that actually was the culprit in taking out much of the soil that much of the soil loss that caused much of the soil loss that plagued a lot of ancient societies. So the question that I want to wrestle with in this book is, could agricultural erosion and degradation limit the lifespan of civilizations? And again, I've probably given away the answer in the title of the book, but I want to share with you some of those stories and some of the data and let you come to your own conclusion. And if you look at recent archaeological studies, there's a lot of work where people have done both the geology and the archaeology, what we refer to as the geoarchaeology, where geologists and archaeologists work together to understand what was happening to the population of a landscape and how that was affecting the land itself at the same time, and trying to put that interdisciplinary perspective together on it. And those studies have been done that showed that soil erosion played a role in the demise of ancient civilizations, ranging from Neolithic Europe, Bronze Age Europe, to classical Greece, Rome, the southern United States, areas in Central America. The list actually goes on. I tried to document as many of those as I could find in putting the book together. I'll spare you all the details today because I could be talking till midnight about that. But there's a number of studies where people have put those perspectives together, and I'll want to share with you some of the commonalities, a few of the stories from it, and some of the commonalities in terms of what you can learn by putting it all together. And the simplest way I could put that is essentially to invite you to think about soil the way a geologist or a geomorphologist like myself thinks about soil. You can think about it as a system, as something that's produced from the weathering of rocks, as rocks break down and are converted into smaller fragments and chemically converted from the primary minerals that the rocks are formed with to the secondary minerals, clays, that plant nutrients are more easily liberated out from. That weathering process combines with the merging of with biological material, organic matter, dead things. And that makes it a healthy, fertile soil. It's essentially the bridge between geology and biology, between the sort of the dead, inert world of the interior of the earth and the living fringe that we're a part of. And so there's this pace at which soils are produced from the weathering and breakdown of rocks and the merging with biological material, with organic matter, to make a soil. And if you're on any kind of a slope, erosional processes are going to be removing that material at the same time. So you have this balance between the production of soil and the local loss and removal of soil. And if you think about soil as a system that way, something that's produced, something that can be lost, and something that is stored on a hillside, you can start thinking of soil on a hillside as essentially nature's bank account. It's nature's capital. It's essentially a storage. You build it up when soil production, the weathering, exceeds the pace of erosion, and you start to draw it down when the erosion exceeds the pace of soil production and reformation. In other words, soil is just like your bank account. If you spend money at a pace faster than you make it, and you do it for too long, you will run out of money. Having done this several times myself, I can vouch for you that theory is true. And if you think about this at the scale of whole societies, that same argument is true for human civilizations in regard to the most fundamental resource we need for agriculture, which is healthy, fertile soil. So if you think about soil the way a geologist does, the time scales are different than your bank account, yes, but that basic mechanics of an input and output and a storage element, what we have on the hillside as a civilization, what you have in the bank yourself, those parallels hold. What is it about agriculture that essentially changed the relationship between soil production and soil loss on the surface of the earth? Well, you can trace it back essentially to the invention of the plow. It's that iconic invention that, when we think of, you turn on a country music radio station, if anyone here does that, and enjoy it as much as I do at times, you will hear, if someone's running through the icons of things. What do farmers do? They plow. It's this iconic symbol of agriculture. But what does it do to the land? It basically leaves the land bare and vulnerable to erosion for some part of the year. It turns the earth. It's intended to suppress weeds and prepare the seedbed. And it's actually really useful for those processes. But if you have, say, a good rainstorm right after you've plowed, you can literally lose a century's worth of soil in an afternoon. And if that goes on for centuries, periodically, every now and then, not every day, of course, but at a slow rate, it can really add up over time, as I'll be sharing. And so the invention of the plow fundamentally altered the balance between soil production and soil erosion on our agricultural lands, the very lands that we need the most to maintain the physical presence of soil as a fertile body. And if we look at examples for that, I could run you through a whole bunch of them. I'm just going to do a couple. We're going to start with classical Greece. And why classical Greece? Well, because geologists and archaeologists have done the work that I could go find and synthesize. Much of what I'm going to be talking about today is not my own research. It's a synthetic effort. I've drawn on the work of many other people to try and put this story together. But when you go look at classical Greece, and you look at the history of the Greek landscape, you can document that cycles of soil erosion and soil formation began right about at the time of the Bronze Age introduction of plow-based agriculture. When the plow came from sources to the east and arrived in the Greek landscape, at the time it was open oak woodland. This is a cross-section. You're looking at the cross-section across a hillside that Tjeerd Van Andel and Chris Runnels put together back in the 1980s. And so if you read that, it's the top of the hill over on the left, bottom river valley down at the bottom right. And those vertical stripes show you essentially the thickness of soil. And typically, the typical thickness on a typical hillside around the world is somewhere between 1 and 3 feet. So a fraction of a third of a meter to about a meter of soil on a natural hill slope is what you'd find in the UN Global Soil Database as sort of the average. And the Greek landscape had a soil mantled cover with open oak woodland that we know of from reconstruction from pollen records from lakes. You can kind of reconstruct what the vegetation is in the region. And this is what Van Andel and Runnels suggested that the Greek landscape looked like at the time between the end of the Ice Age and the arrival of the plow. What then happened is that cultivation spread up onto the hillsides. Typically in societies, the river valleys are the first to be plowed and planted. Why? Well, it's sort of flat, well-watered, easily worked land right by a river. That's where you would start. As populations grow, farming tends to spread up into the upland environments, and by the peak of the Bronze Age culture in classical Greece, farming had spread from the river valleys up onto the hillsides. And so you had cultivated fields across the landscape, and erosion started to outpace the pace of soil production. What they worked out was that over time, the soil that had been on the hillsides ended up down in the valley bottoms. Some of it slid off, like is illustrated here, some of it eroded off fairly slowly. But if you think of, and you can still find areas today in the Greek landscape where you can find Bronze Age agricultural implements up on hillsides that have been essentially eroded down to virtually bare rocky soils, or the bare rock, the remnants of soils. Not places you could actually farm today. And if you think about the problem of how you actually support a population through agriculture, it turns out that if you take a thin layer of soil that has a large surface area you could work, and you erode it off and stack it all up in the valley bottoms in a small area, even if the volume of soil in the landscape remains the same, it's the surface area that matters in terms of how much you can actually work. If you strip it off and put it in a deep pile, then you could maybe work it for longer, but you're not going to be able to support as many people with as extensive a farm. So that's essentially what Van Andel and Runnels argued happened to the Greek landscape, although they didn't quite frame it the same way. They did, though, look at the population density of the southern Argolid, the particular region in southern Greece. And this is the graph from their work that really got me started in thinking about the kind of direction that I went with the background research in putting this book together. And what it shows you is the population in this area ranging from 6,000 BC over there on the left over to the contemporary world on the right. And there's two interesting features to a graph like this. And you notice each one of those black dots is a point in time where they felt through the geoarchaeological work that they did that they could constrain this kind of an estimate. And you'll notice that the curve sort of starts low at the start of the Bronze Age, it rises to the Bronze Age, it drops into a dark age before the age of classical Greece, the population goes back up again, it drops again for another dark age before the modern age. And of course the question that you might be asking yourself, seeing a pattern like this, is what's going to happen over on the next thing to the right. But there's two aspects to a graph like this that I found really interesting. Well, one was really interesting, one is actually fairly trivial. The trivial one is, why does the amplitude of that signal go up with each cycle? You know, in the Bronze Age it's lower, it goes up in the Classical Age, the Modern Age is higher, and the simple answer to that is technology. Agricultural technology that we have today is far more sophisticated than what they had in the Bronze Age. There's no mystery about that. You can support more people on the same side from the same size farmland today than you could 6,000 years ago. There should be no mystery about that. The part that intrigued me about this graph is what sets the periodicity. Why this rise, fall, rise, fall, rise, and then, as I mentioned, what's going to happen off to the right-hand side? Why does it take a few thousand years in between civilizations being able to apparently reoccupy the same bit of landscape? That was the question that got me wondering, well, could soil loss and soil erosion does it occur at a pace that is actually commensurate with pointing to a figure like this and inferring some kind of a causal link. Now, of course, there were not geomorphologists running around in the Bronze Age trying to measure soil loss off of fields and publish it in obscure academic journals. There's not that much data that we can go to outside of the triangulation of the geoarchaeological world, which is the kind of data I was just showing you. But that doesn't mean people weren't paying attention. Plato, back in the 3rd century BC, the classical Greek philosopher, noticed the problem of soil erosion off the Greek landscape. He was looking at the evidence for the Bronze Age soil erosion event when he wrote in one of his dialogues that the rich soft soil has all run away, leaving the land nothing but skin and bone. But in those days the damage had not taken place. The hills had high crests, the rocky plain of Phelus was covered with rich soil, and the mountains were covered by thick woods, of which there are some traces today. He was looking at things like olive trees on the pillars around where the farmers had plowed. The Greeks were very into plowing their fields. And Plato made the argument quite explicitly that the Greek landscape in his day, at the age of classical Greece, was not able to support the same populations that could support the same size armies as they had in prior days because of the loss of soil off of the landscape, as he was describing here. As far as I can tell, he's the first person to explicitly make the argument that the way that people treat land, in the end, sets how the land will be able to treat a society. He didn't get full credit, I think, for this idea for many years until the geoarchaeological work was done thousands of years after his time, in part because he wrote about this in the same dialogue that he discussed the history of Atlantis. It was not viewed as the most credible source in the classical world for that reason. Now, if we leave the Greeks and we go to the Roman civilization, we can also make a tie between soil erosion and then sort of the history of classical Rome. There's a Princeton University professor, Sheldon Judson, who back in the 1960s apparently really liked to go to Italy and do his summer field work there, and he did a fair amount of work looking at studying erosion rates in antiquity off of the Roman heartland in the area of central Italy. What he's able to document was that erosion rates in the Roman heartland increased by an order of magnitude starting in about the 2nd century BC. And how did he do this? Well, he did things like he went to Roman monuments where the foundations were now exposed. And what's the one thing you don't do when you build a foundation? You don't build it above ground, you build it below ground. That's the whole point of a foundation. So if you go around to classical monuments that we know the date that they were actually built in, you measure the height distance between the top of the foundation and the modern soil, you can constrain how much soil has been lost since the thing was built. It's a pretty good indicator. The other way you can do it is you can drill cores into lakes, radiocarbon date the different layers, back out how much was going in from a known area contributing to the lake, and figure out the erosion rate. He did things like that. It's the kind of stuff geologists like myself would do. But that doesn't answer the question of, okay, well, what happened in the 2nd century BC? And the short answer is that Roman agriculture changed in a very profound way about this time. Prior to this period, Roman farms were primarily small-scale polycultural farms that practically had multiple canopy, diverse crops, and in the 2nd century BC, you might recall the wars with Carthage that Rome had, where they sort of went after their geopolitical rival across the Mediterranean. And you've probably all heard the stories that the Romans, when they sacked Carthage, they salted the soil to famously try and keep it from being farmed. What you don't hear that much about is that they also brought several 100,000 slaves back to central Italy, and it totally changed Roman farming. It went from being small-scale farms to very large-scale monocultural plantations, a transition in agriculture that might sound fairly similar to what's happened in the United States over the course of our recent history. What did this do to the landscape? It started erosion rates coming at a much higher rate than had been happening before. And what you don't hear in the history of Rome so much is that by about the 1st through 3rd centuries AD, just about 300-400 years after the sacking of Carthage and the fundamental change in Roman agriculture, the fields of central Italy were no longer able to feed the populace in Rome. It was North Africa and Egypt that were essentially the essential sources for feeding Rome in the late days of the empire. In fact, it was a capital offense to actually interfere with the grain shipments from North Africa to central Italy because the political stability of Rome depended upon free bread and circus in the capital. So the 1 million people or so in the capital in Rome were being fed by farms in Africa. In other words, the Romans went back and started working the fields they had salted several centuries before to feed the late stages of their empire. So it was the extensive olive and cereal plantations in Africa that were supporting Rome near the end of its days. And again, this is not new. This is not new information. There's a gentleman named Walter Loudermilk, who was a Soil Conservation Service scientist back in the 1930s through 50s, who, in the days before the Second World War, got very interested in the aftermath of the Dust Bowl about what had happened to soils in the classical world. And he took a tour from the Middle East across North Africa into Southern Europe, trying to look at the state of soils and what had happened to societies that had, in his view, abused their soils in the past. And when he went to North Africa and to Timgad in Libya, he found that the second largest city of the Roman Empire that day, if I'm recalling this correctly, a city that had 60,000, 70,000 people in it at its peak and was surrounded by rich agricultural fields, when Loudermilk visited it right before the Second World War, he couldn't find any soil on the hillsides. In his words, he wrote that over a large part of the ancient granary of Rome, we found the soil washed off to bedrock and the hills seriously gullied as a result of overgrazing. He also found some olive plantations where the soil had been protected on the hillsides, where trees were where you could still grow crops, and he therefore concluded that it hadn't been a climate shift that had destroyed agriculture in northern Africa, but it was essentially the long-term loss of the soil that had prevented its productivity. Now, what is it about the practice of plow-based agriculture that we can point to as a likely cause of this kind of long-term soil loss over fairly large portions of the landscape? And I'll point back to my own home state of Washington to show you this picture of a winter wheat field. You'll notice there's no crop out at the time, but it's been recently plowed and had a rainstorm. Those little channels that are cut into it are things we call rills. They're not gullies. A rill is something you can plow over with a tractor. A gully is something you don't want to drop your tractor into. It's a question of scale. And these kind of little channels, these little rills that can actually be, erased with a little work on an annual basis, to a geologist like myself, it's a picture of soil simply bleeding off of the landscape. Why? Well, it adds up. If it happens year after year, and again, this is a winter wheat field. If you have a field that is bare and vulnerable to erosion by wind or rain, if that wind or rain comes during that period, you can really lose soil at a pace that is frankly unsustainable. And this is also from that same area in the Palouse in eastern Washington. It's an area with loess soils, if people are familiar with the term. It's a wind-deposited soil, fairly easily erodable. Silt would be the other word for it. And this shows you a farmer's field, again a winter wheat field, that shows with that fence in the upper left-hand corner is a fence that the farmer built around his water cistern when he first broke the sod on this area back in 1911. The only thing that happened to this field between 1911 and 1961, when this photograph was taken, was that it was annually plowed and planted in winter wheat. And you'll notice that there's a bit of a cliff there behind, to the left of that fence. What you may not be able to notice is that there's sort of a washed out little vertical line that shows you a stadia rod that doesn't show, a survey rod that doesn't show up on the negative very well. But basically that's a 5-foot drop. What this shows you is that there's been 5 feet of soil loss between 1911 and 1961 off of this field. Those little rills add up over time. 5 feet in 50 years, that's what? That's about 1 foot a decade. That translates to about an inch a year. There's nowhere on Earth that soils form as fast as an inch a year under natural processes. You heard yesterday, several of us say that it takes centuries for nature to form an inch of soil. Well, it can take less than a century for farming practices to erode off feet of soil. Now, you should also be sitting there, or whether you're here or wherever you are watching this, you should also be questioning, well, isn't that pretty extreme? Well, of course it's extreme. That's why I'm using it as an example. You should be asking yourself, how typical is it? That should be the next question for me in your mind. And I'll show you some data in a minute that actually puts some perspective on that. But we can also look at sort of wholesale loss of soil across fairly broad regions, like the Piedmont region of the southeastern United States. So the map that's up there now shows you the area from Virginia down to Alabama, and that colored noodle, the gray and black, and then a bit of the hatchet area, shows you the Piedmont country, the upland country, the hill country. So not the coastal plains, not the Appalachians, but the rich farmland, or the originally rich farmland in between in the Piedmont. And what this shows you is the reconstruction of how much soil has been lost since American colonization of the region, so over a few centuries. And you notice that most of it's gray or black. That means that between somewhere north of 4 inches of topsoil has been eroded off, and in some of those areas, more than 10 inches. How big a deal is that? Well, there was only about 12 inches of thick, rich, black, fertile topsoil across this region to begin with. So if you think that we could erode off fully a third to darn near all of the original topsoil that supported those rich harvests of tobacco that got the American colonies economically viable to begin with, if we could erode off much of the soil that was the ultimate source of that wealth over the course of a couple centuries, imagine what the Greeks and Romans could do with substantially the same technology. The plow has changed in the last few centuries and millennia, but the basic idea of plowing hasn't. The basic idea of leaving the land bare and vulnerable to erosion hasn't changed that much. And so if we could do this in magnitude of work over a few centuries, think what other societies could do with a 500 or 1,000 year or 2,000 year run at it. It starts to sound like, well, maybe this idea of long-term soil loss off of large areas of the landscape may not be such a crazy idea after all. And in fact, George Washington noticed in colonial times the problem of soil erosion off of his own and colleagues' fields. He actually put a lot of work into trying to defeat gullies on his own land. And in a 1796 letter to Alexander Hamilton, Washington wrote that if a few more years of increased sterility will drive the inhabitants of the Atlantic states westward for support, whereas if they were taught how to improve the old instead of going in pursuit of new and productive soils, they would make these acres, which now scarcely yield them anything, turn out beneficial to themselves. Washington was decrying the long-term degradation of the land under colonial agriculture. What was the issue there? Essentially, growing tobacco the way it was grown in colonial times was quite erosive. You could only get about 3 to 5 years of productive crops out of a piece of land before you essentially, the yields went down, you lost the topsoil. The problem was, of course, erosion. If you've been in the southeast during periods of intense rainfall, you can kind of get the idea of what could happen with that field that I showed you from the Palouse might not be restricted to eastern Washington. And so this problem of being only able to work a small piece of, a piece of land for a few years led to the rise of plantation agriculture as the way to be economically viable, whereby moving cropping around over a large area over time. But the degradation of the land that followed that was something that Washington predicted that American society would be compelled to move across the Appalachians in search of fresh, fertile soils, because a nation of farmers couldn't, the one thing that they could not afford to do was so thoroughly degrade their land that they were not able to actually continue farming. Washington's prognosis turned out to be fairly viable. There was a major soil erosion contributed to the major push westward, and this was long before there was discussion about any kind of a manifest destiny to transform this continent. A lot of the push west was actually impelled by degradation of the land that we first started farming on the eastern seaboard. Now, I ran into a study from the 1920s that I think really captures very well the answer to the question of why would a nation of farmers so degrade their land as to imperil their ability to continue farming into the future. And Anthony Craven wrote in his paper that men may, because of ignorance or habit, ruin their soils, but more often economic or social conditions entirely outside their control lead or force them to a treatment of their lands that can end only in ruin. In other words, what Craven was arguing, which I think is still valid today, is that farmers often find themselves in social and economic contexts that lead them to prioritize short-term returns off their land over the long-term ability to sustain agricultural productivity. And this has been manifest whether it's in terms of tenant farming, whether it's in terms of corporate farming, whether it's in terms of overcapitalized private farmers desperate to pay off their banks and not lose their farm. There's a lot of situations that essentially can lead farmers to prioritize short-term production over long-term maintenance of the productive capacity of their land. And Craven was onto that, almost a century ago. But getting back to that question in terms of the image that I showed you of the Palouse, that really rapid erosion of an inch a year and advertising that really was extreme, let's go back for a few minutes and look at what kind of rates of soil loss are at a global scale today. How extreme was that example that I showed you, in other words, and what would be the typical number you might want to actually use to think about in terms of long-term policy implications. So in researching this book, I was asking myself exactly the same question and trying to figure out, okay, well, what are the typical rates? And so I did something that's actually gotten to be very difficult to try and get students to do anymore. And that is, quite simply and quite frankly, I went to the library. And what did I do? I gathered all the data that I could vacuum up over the course of about 3 weeks on what are the rates of long-term soil loss off of agricultural fields today. I mean, we have geologists and agricultural engineers and scientists measuring rates of soil loss in fields in different parts of the world. I also gathered up data in terms of long-term rates of soil erosion. If you think about that balance between soil erosion and soil production, if you can constrain the rate at which landscapes erode over the long term, the geological background, that gives you a number to compare the modern numbers against and try and figure, okay, what is that balance? Because in our experience, most parts of the world outside of sort of the arid areas and the alpine areas tend to be clothed in soil. That means, therefore, that soil production is keeping pace with soil erosion. So if we measure long-term rates of soil loss off of natural landscapes, we get an idea of what long-term rates of soil production must be. We can constrain them that way. We don't measure them directly, but we can put sideboards on them. So I basically did that. I went to the library and I tried to gather as much data as I could find. What did I get? I found 1,402 studies. Why did I stop at 1,402? Well, first, that was a lot of work. And secondly, I don't think we could keep adding numbers to this, but as you'll see, I don't think it'll change the story a whole lot. And third, that's all the time I had. My students were out in the field doing their own work. By the time they got back, I got busy again, of course. And so I got 1,400 studies of agricultural erosion rates and long-term geological erosion rates. And that sort of note across the bottom there, I did not include any universal soil loss equation-based model studies. This is real data. This is not data that somebody predicted using a model. This is data somebody measured from stuff coming off of a field. And you'll notice that I've got one axis to this graph, and I'm only going to show you sort of two data graphs here. This is the first one. Well, I'll show you a version of this again in a moment, but where I modify it a bit to make a point. But there's one axis across the bottom, it's erosion rate. And you'll notice it occurs in log cycles of 10. So each of those increments along that axis is a power of 10. It's just like the Richter scale for earthquakes. So you'll notice that there's many orders of magnitude variation in erosion rates on this planet. Over at the left-hand side, we're dealing with things that happen at a pace of like a 10,000th of a millimeter a year. I challenge you to figure out a way to measure something that happens that slowly. It's hard to do. Over on the right-hand side, the fastest eroding areas on the Earth erode at a pace of about a centimeter or 2 per year for natural erosion. You get up close to a meter in some agricultural settings, but those are really extreme. Those white data points that are labeled cratons, soil mantle terrain, and alpine and glaciated terrain, those are data points that are from long-term geological erosion of natural landscapes. And does everybody know what a craton is? No, it's not something that goes into a salad, right? This is a geological term for a flat, tectonically dead part of a continent. Think about a place where mountains are not being pushed up. It's the American Midwest. It's the heart of Africa. It's most of Australia. It's the Amazon basin. It's places that are tectonically relatively inactive. They tend to be low relief, gentle terrain, and they erode quite slowly. They had a maximum rate, as you'll see on the graph, of about a hundredth of a millimeter a year. Soil mantled terrain, that's places like the rolling hills of California. The Piedmont region in the southeast that I talked about. You can think of it as rolling hills with a soil mantle, the classical Greek landscape that I was talking about. And notice that those areas erode at a pace that reaches up to about a millimeter a year. Your fingernails grow faster than that. We're still dealing with fairly slow rates in terms of soil production. The alpine and glaciated terrain over there on the far right-hand side, those are the parts of the world that erode at paces that exceed about 1 millimeter a year or so. And that number will come back. And what do we mean by alpine and glaciated? I mean like the Alps. I mean like the Himalaya. I mean like the high Andes, the Cascade Range. Real mountains, places we don't tend to farm. So, and that data all across the top, those little black circles labeled agriculture, those are erosion rates off of agricultural fields practiced under conventional plow-based agriculture. And you'll notice that if you play the game of which of the natural landscapes does the agriculture most fit, you can come to the conclusion that conventionally plowed farms erode like alpine topography. We've actually managed to turn places like Nebraska and Kansas into places that erode like the high Himalaya. If you think about it, that is quite an achievement. It's not necessarily one to be proud of, but it is quite an achievement. You also notice that the places, that vertical bar, that red bar that I've now added, is the USDA's soil loss tolerance value range that ranged from about 0.4 millimeters a year to about 1 millimeter a year. That's the range at which has historically been pegged as acceptable rates of soil loss based on the economics of farming in the 1950s when those values were established. And you'll notice that it plots at the very far right-hand side of all the long-term natural soil loss data from the cratons and soil-mantled terrain, the places in the world that we actually farm. So in other words, conventional agriculture is not sustainable in soil-mantled landscapes. So the two take-home messages of this, what I call sort of a brute force data compilation, is that if you look at the rates at which natural landscapes around the world erode, and you look at the rates at which conventionally farmed plow-based agricultural, with plow-based agricultural methods work, they don't add up. Conventional agriculture under plow-based agriculture, ranging from fully mechanized farms to non-mechanized farms in the developing world, the problem is leaving the ground bare and vulnerable to erosion. That was the bad news slide. What I want to show you here is essentially the good news slide. And this is the last graph with data that I'll show you, I promise you. This one has two axes. So the vertical axis now is erosion rates. The x-axis is essentially a percentile plot. So what I'm showing you is all the data that I compiled out of that library excursion, which frankly is nowhere near as much fun as doing real field work, but it can be, you get a lot more data faster this way. So I'm showing you all the data. It ranges from the smallest values on the left to the median or average value in the middle, where it says 50%, and then the highest values over on the right. So it's just a way of spreading out the data so you can see what's behind the argument that I'm making. And so what you can see is that that red bar going across is that same red bar from the last graph. It's the soil loss tolerance values, 0.4 to a millimeter a year. And those black circles that plot above everything else, that is the conventional plow-based agriculture data. The black line that is further down, that's the compilation of all the long-term geological erosion rate data. Now I've added 3 other kinds of data sets that I also compiled, but I haven't told you about yet, to this graph. And what are they? Those circles are long-term rates of soil production. Geologists have cleverly come up with ways of actually quantifying the rates that soils are built up using isotopic and geochemical methods. And so I compiled as much data as I could find on that, threw it on the graph. There's long-term rates of erosion under native vegetation, sort of erosion rates off of parks, off of places that are not agriculture, are not disturbed by human activity, and those are the little white triangles. And the little white diamonds are areas where the good news lies, because those are erosion rates off of agricultural fields where conservation agriculture is practiced. Things like no-till farming, things like terraced farming, farming that prioritizes soil, the minimization of soil loss. And you'll notice that all those sort of white data points play right on top virtually on the long-term geological erosion rate data. In other words, agricultural soil loss doesn't occur because humanity farms, but it arises from how we farm, from using the plow. There are agricultural methods and techniques and then those little white diamonds on there that show you that we have it within our power to farm intensively in ways that do not result in the wholesale soil loss that has plagued ancient societies. The problem, of course, is that those methods are considered alternative agriculture. Now, if we look at sort of the importance of this and how these numbers add up, we can look at those numbers that I just showed you in a different way. We'll just look at the average values, whether you like a median or a mean. Take your pick in terms of which average you like. It makes no difference to the argument that I'm going to make, so I'll show you both. And you'll notice that for conventional plow-based agriculture, the average erosion rate off of fields worldwide in this data compilation is somewhere north of 1 millimeter a year. Those red numbers on the screen. The numbers for rates of erosion under conservation agriculture, under native vegetation, rates of soil production, long-term geological erosion rates, all those are below about 1/10 of a millimeter a year, all those blue numbers. And I'm not going to argue to you that I'm going to parse anything between the different sets of blue numbers. What I want to do is say, okay, look at those numbers. The red things are a lot bigger than the blue things. And if you give me basically the argument that conservatively, the difference is more than 1 millimeter a year on average. We can then, and I think it's a conservative argument given those numbers that I'm showing you, we can basically plug that into the kind of back of the envelope calculation that it's fun to do with graduate students sitting around with a beer over and trying to go, okay, well, how serious is this kind of a problem? You can take that millimeter a year net soil loss off of agricultural fields as a global average and look at it in terms of what happens to the typical 1/2 meter to 1 meter thick hillside soil. How long would it take to actually plow or erode through that full complement of a native endowment of fertility in most landscapes? Well, it would only take about 500 to 1,000 years at that rate to quite literally burn through the soil off of a landscape. And that is starting to line up with what we saw in the Piedmont, what may have happened in the heartland of Rome, what happened in classical Greece. That range, 1,000 years plus or minus, is about the longevity of most major agricultural civilizations outside of a few major exceptions. And those are the major river floodplains along which agriculture first arose for reasons that I also go into in the book. Places like the Tigris and Euphrates in Mesopotamia, the Indus and the Brahmaputra in India, the Nile in Egypt, the major rivers of China. Those places are parts of the world on major river floodplains. They're annually fertilized with an endowment of silt derived from erosion off of the uplands. And if you think of, well, what's upland of the major rivers in China? What's the Tibetan Plateau and the List Plateau where they have huge erosion problems today? What's upstream of Mesopotamia? It's the Zagros Mountains where agriculture first arose, which are not exactly an agricultural powerhouse today. What's upstream of the Nile in terms of it's not regions of the world that we view as incredibly prosperous given the long-term soil loss that has happened in them. So the exceptions, the long-lived human societies where we've actually worked the same land for thousands of years, are actually in places where the physical geography is set up where they're subsidized by soil loss off of their uplands. Now, again, I'm not the first person to make this argument. The guy named Walter Loudermilk, the guy who went around North Africa in the late 1930s, wrote about this in the 1950s when he wrote that here in a nutshell, so to speak, we have the underlying hazard of civilization. For by clearing and cultivating sloping lands, for most of our lands are more or less sloping, we expose soils to accelerated erosion by water or by wind. And in doing this, we enter upon a regime of self-destructive agriculture. Loudermilk was basically arguing that soil loss had contributed to the demise of many ancient civilizations, and I think he was right in the money with that. Public interest in the problem of soil erosion in the United States obviously was accelerated by the Dust Bowl in the 1930s, and President Franklin Delano Roosevelt in 1937, in a letter to the governors of the then all 48 states, wrote that a nation that destroys its soils destroys itself. His words, I think, are as true today as they were back in the 1930s, but I think they have even more weight, if you will, if we think about this problem as a global problem. We don't have any new places to go to actually try and work sort of new, fresh, unworked agricultural soils. We're already farming pretty much the whole part of the world that we would be able to farm over the long run in the end anyway. So this obviously motivates the question of, is soil restoration possible? Could we actually reverse the long-term historical pattern of soil degradation? And as I was talking about yesterday in our yard, my wife, Ann, my co-author on The Hidden Half of Nature, really taught me how fast people can restore soil if we apply the things that we have at our disposal. organic matter, labor and energy, and some biological assistance through the microbial world. In other words, we can rebuild soils surprisingly fast, a lot faster than nature does. It may take her 500 years to 1,000 years to build an inch of soil, but Anne showed me that she could build a couple years of soil, of reasonably fertile soil in our yard in less than a decade. And there's some societies that I didn't talk about yet, but I write about in the book, that actually built soils over the long term. And fertile carbon-rich soils have been built by anthropogenic activity in both the Amazon and reclaimed seabeds in northern Europe. The famous Plowed soils in Europe shown there on the screen are, you see that rich black earth overlying what used to be beach sand. When the Dutch started to get hemmed in by their neighbors and their population kept going up, they started to reclaim land from the sea. How did they do it? They walled off parts of the sea, drained it, and then they returned their urban organic waste, organic matter, back to the land very aggressively over the course of decades to build what are today still some of the most fertile soils in Europe. They built those soils essentially by hand. Native Americans in the Amazon basin built the famous terra preta soils, the black earth of the Amazon, in an environment where if you go and just dig randomly in the forest, you tend to find very poor soil. Why? Well, in that environment, the organic matter that falls to the forest floor tends to get recycled fairly fast. It doesn't build up so much in the soils. The natives of the region essentially used the ashes from their cooking fires and their waste, returned them back to their fields to build the fertility of their soils in ways that basically produced the most fertile soils in the Amazon that sadly today some of them are being dug up and exported to the urban environment and sold as potting soil. The point that I want to make though is that human activity can actually build fertile soils even as we use those soils to produce food for ourselves. It's all about how we do it, how we farm. Why would we bother trying to restore soils at a global level? Well, I'd argue that it's to address some of the major global challenges of the 21st century. Because restoring healthy, fertile soils to the world's croplands on a large-scale basis and restoring much of the cropland that has been degraded could help us feed a post-oil world. This is going to be a challenge, and we need creative solutions for it. Soil restoration could help with that. It could help us with carbon sequestration and dealing with wrestling with the issue of climate change. There's actually a lot of potential to store carbon back in soils to rebuild the soil organic carbon levels. Restoring soils could help with public health and city livability and could help with the problem of biodiversity and environmental degradation, again, as we were talking about and mentioned last night. Now, restoring soils and the fertility of soils isn't going to solve all of those problems, but it could be a foundation for partial solutions to all of them. There's very few things I think that you could propose as singular actions that could contribute to the full spectrum of environmental problems that we're facing in this century. Soil restoration, I think, could be the foundation for efforts that could help with each of those. In terms of the question of feeding an agricultural world, we're really sort of at the time of peak oil. Whether it's now, a few years ago, a few years from now, is probably not the question. The question is really how are we going to maintain agricultural productivity on the far side of the peak oil production curve as we face a growing human population. It's projected to peak out at somewhere between 9 and 11 billion people by about 2100, and you can choose your own demographic projections, if you will. But the problem is we're going to have more people to feed, and if we continue degrading agricultural land at the pace we have in the past, we're going to face an even greater challenge keeping the world of the future fed than if we were to even maintain the soils that we have today. Increasing the fertility and productivity of the world's degraded soils could help us with that problem. And the problem can be captured in terms of, well, how are we going to feed a post-oil world without cheap fertilizer-intensive agriculture? If the cost of fossil fuels continues if it rises this century as one would project from the potential supply limitations that may be coming down the road, the question of relying on 10 calories of fossil fuels to produce 1 calorie of food starts to become sort of bad math. How will we actually try and maintain production? Well, a number of us have called for changes in agricultural practices. You could call it a brown revolution, a greener revolution, a new agricultural revolution. There's lots of labels that this could go by. But the idea of using cover crops and diverse crop rotations to boost to maintain crop yields and to minimize inputs. And the use of that with no-till farming and or organic farming, and particularly the combination, which still needs to be worked out in some ways, that can actually compete with conventional agriculture in terms of yields. There's a transition period, but it's actually it's shockingly short, in the order of 3 to 5 years from the studies that I've seen in terms of the time scale to transition from conventional practices to organic without much of a loss in yield. And those practices can also greatly exceed production using conventional techniques on degraded land. In other words, we could think differently about how we try and restore some of the land that's been degraded by agricultural practices. And if you think about the problem, rebuilding soil and soil fertility on degraded land is really going to be essential for sustaining agriculture in a post-oil and therefore post-cheap fertilizer world. When that world arrives, whether it's in 20, 30, or 200 years, is simply a question of the matter of time scale. We need to be thinking ahead of the curve so that we can proactively change practices so we don't turn what could be a problem into a crisis. If we think of soils and climate change, the thing that I mentioned, I think, last night that a few people are aware of is that by the late 20th century, fully a third of the carbon that had been added to the atmosphere since the Industrial Revolution came from degradation of soil organic matter. It came from plowing up the plains in the American Midwest, in Eastern Europe, in Western China. So a lot of carbon that has been added to the atmosphere didn't come from fossil fuels. It came from the degradation of the rich store of soil organic matter that we have in this world. There's twice as much carbon in the world's soils as there is in the atmosphere. If we can rebuild the carbon content of our agricultural soils, it will help to draw down carbon from the atmosphere. The question is how to do it and how much we can put back in. Well, that depends on how we practice agriculture. If we could practice agriculture in ways that are tailored to greatly increasing soil organic matter, there's several ways to do that. No-till agriculture, cover crops, basically stopping plowing is would be a major contribution to that. And so would the idea of biochar, the idea of taking organic matter, pyrolyzing it or burning it in a low oxygen environment to basically produce charcoal, which is highly concentrated carbon that is relatively inert, takes a fairly long time to break down, and can serve as microbial hotels that actually help spur fertility and nutrient cycling, like I was talking about yesterday. Estimates for how much how much carbon can be sequestered in soils vary quite a lot depending on who you're listening to on it. The point that I want to make today is that we have opportunities to actually rebuild the carbon store in soils that would help not just sequester carbon, but help rebuild the fertility of soils. Ron Amundsen, for example, the soil scientist at UC Berkeley, 14 years ago, noted that cultivation and deforestation releases about 4 gigatons of carbon per year into the atmosphere. That's equivalent to more than half of global fossil fuel emissions. In other words, the practices we have on the landscape are a big problem in terms of carbon emissions on a scale that starts to be comparable or a good fraction of what it is in terms of fossil fuel emissions. In other words, the carbon problem is not just about tailpipes, it's also about how we treat land. And Ratan Lal, a decade ago, the eminent soil scientist, wrote that he estimated that changes in agricultural practices could actually offset on the order of 10% plus or minus half of global fossil fuel emissions. That could be actually a good down payment in terms of reducing emissions. It's not going to solve the carbon problem, but it could help not just solve, it could be a down payment that would also help solve the soil fertility problem. In other words, what I'm basically arguing for is that it's time for a new view of the soil. We need to think about soil in a different way. We need to think about it not in the ways that we have thought about it as we've created the problem that we have with soils today. So how have we thought about soils in the past? Well, for much of our existence, we thought of soil as a mystery. Fertility was to be personified, deified, and revered. This is Ceres, the goddess of cereals, the goddess of grains. And for a lot of our history, we viewed soils as that kind of a mystery. We also viewed soil as a means since we have been farmers for the most of our history, most of us viewed soils as a means to a living. Land was there to be worked. That's as true for farmers today as it was in the past. The question, of course, is how we work the land. But come the Renaissance, soil started to be viewed as a decipherable mystery. It was something we could study, something we could understand. And the famous words of Leonardo da Vinci, who wrote that we know more about the movement of celestial bodies than about the soil underfoot. His words are as true today, 500 years later, as they were when he spoke them in his day. We've learned a lot about both realms, but the things that we're discovering today about the universe of microbial activity in soils and its relationship to fertility of the soil and the health of plants is exploding in a way that shows just how far we still have to go in terms of understanding fully the processes in the soil. In the 19th century, we came to view soil as a chemical reservoir, a medium to be fertilized pretty much as needed. If you just added the right elements to the soil, it could bolster crop production. Fertilizers were very effective at boosting soil production on the already degraded lands in Europe and North America. They seemed essentially they seemed like miracle cures for flagging soil fertility, but they came at a price, and they had a very limited perspective that didn't look at the biological basis for soil fertility in many of the world's soils. In the 20th century, we started to look at soils as an industrial commodity, something to be used and used up. What do you do with the least valuable input to any industrial process? You don't worry about conserving it. That's the part that you use up. We tended over the course of mechanization and industrialization of agriculture in the late 19th and throughout the 20th century to basically think of soils that way. We didn't think of them as the most fundamental and valuable or invaluable element of agricultural production. We thought about them as essentially the least expensive aspect of it. Today, over the past 20 years or so, we've started to actually realize how much soil really is in itself an ecosystem, and it's something that we could actually understand and work with in terms of agricultural production by trying to actually partner with our microbial allies in the soil and to be perhaps more clever in an ecological sense, in the scientific definition of ecological thinking, in terms of maintaining diverse crop rotations and not being predictable in our rotations in terms of pest management and all kinds of elements for aspects and techniques of biological pest control. There's a lot of things we can do in terms of applying soil ecology to defining the future of agriculture. And I think we need to integrate the insights of soil ecology with agricultural technologies if we are to feed the world based on ecological processes and nutrient cycling. And to me, this is really the challenge of the 21st century. How do we actually it's not a question of sort of going back to ancient farming practices. I mean, after all, those are what did in Greece and Rome. The question is, how do we actually take the kinds of scientific knowledge that we have today and the agricultural technologies that we have access to today and use them in ecologically wise and intelligent manners to foster and maintain long-term agricultural production. And I think there's some guidance that we could take from the principles of conservation agriculture. As laid out by the FAO, you can think of it in terms of three basic elements that a long-term sustainable agriculture would need to have. Minimal or no disturbance of the land surface. That could be a direct planting of seeds or no-till agriculture as an element of that. Permanent ground cover, retaining crops that including cover crops and rotations, and planting diverse crop rotations to maintain soil fertility, but also to break up pathogen carryover. Each of those things individually won't solve the problem. Doing all three together gets us a long way down the road towards solving the problem. And I'll suggest to you that that's not, in that context, it's not really a question of low-tech organic versus GMO and agri-tech. I think that's far too simple a dichotomy to actually lay out. The question, I think, is really of how to apply an understanding of soil ecology and soil building to the applied problem of profitably increasing and sustaining crop yields in a post-cheap oil environment. And frankly, I think we're going to need sort of all the tools in our quiver to actually be able to pull this off over the next century. But I think we need to reframe some of the discussion and argument about how is it that we're going to intelligently apply the science that we have at our disposal, which we are not doing today in the broad sense, to the long-term problem of sustaining soil as an ecological system and promoting the life within the soil as the root and source of the life above the soil and the production of crops that we need to sustain ourselves. So healthy soil, I think it's not a silver bullet for solving the world's environmental problems. I'm by no means suggesting that. But I do think it's a secret weapon. Why is it a secret weapon? Well, because we're not actually really using it at a policy level in a way that I think that we really could. But because restoring soils could really help us address the problems of feeding the world, the problem of climate change, the problems of public health, our physical, mental, and social health, the health of the food that we eat. All those problems, I think, solutions to all those problems could be founded, need to be founded, in a long-term respect for healthy, fertile soil and efforts to actually rebuild for healthy, fertile soils. Because healthy soil is the foundation for human health and the foundation on which environmental health are to be built. It really does all start with the ground beneath our feet. And finally, I think that the first and foremost argument for soil restoration, it means, quite frankly, we have to stop treating soil like dirt. Thank you. And I think we have a few minutes that make questions feasible.
Great. Thanks for the presentation. Terrific. Two questions. One is, if you just left the soil, untilled, and you put seeds down, wouldn't the very wind and rain that you worry about causing the erosion just blow the seeds all over the place? And yeah, it would grow anyway?
The key is to leave the stubble from the previous crop on the surface, and that serves as essentially a mulch that helps to cut down on erosion. It helps to increase infiltration. It decreases exposure to the wind. So the trick is you don't leave the ground bare. You basically leave it covered.
Great.
So the short answer is keep it covered.
Got it. Okay, that makes sense.
Yeah.
The second question is regarding the CO2 effects of plowing and what it does to the environment and the ozone and that makes sense. And my question that I have is this thing I've always heard the last few years that the methane gas from cow farts is actually worse for ozone depletion than all of the fossil fuels burned in all the cars, trucks, and airplanes around the world. Can you talk to that?
A little bit. There's a great new book that just came out called Plowed that I would say, for all things cows, I would recommend that you get that book and check that out. I'm not going to be the expert on cows, but there's a couple things. I have seen studies that have suggested that methane from agriculture, which would include that, is greater than methane from fossil fuels. So if you're dealing with CO2 and methane, you're dealing with different possible solutions. The other thing that if I'm recalling what I looked into in terms of that issue, that it's the other end of the cow that the methane's coming out of.
Oh, really?
Yeah, it's the front end, not the back end. And so it's digestive problems. I think a lot of those problems, as I understand it, are coming from feeding cattle corn as opposed to grass. And so okay. I think there's actually a fairly simple solution to that problem. Again, I'm not an expert in this, so take what I'm saying on this with a major grain of salt, because the old memory is not what it used to be. But my recollection is both those things, that essentially if you change the diet of cows, it would have a huge effect on that problem.
Okay. Well,
if you change their diet to what they actually are supposed to eat,
sure,
it would have a big effect on it.
Thank you for all your work.
Thank you. Do you know the author? Yes, Dennis Hayes and Gail Boyer Hayes. It's a great book. It's a fabulous book. It came out in March of this year. I highly recommend it.
Thanks very much for your presentation and for your book. The conventional wisdom, as I understand it, with respect to animal agriculture or grazing animals on land was that was damaging to soil, but there's some recent work to suggest the opposite, that it's good for soil. I wonder if you have an opinion on that.
Yeah, that I actually do. I think the effect of grazing on soil and soil health completely depends on how you do it. Because there's very compelling evidence that sort of overgrazing can degrade soils. There's really no argument with that. There's been some very interesting work over the last couple decades where people have been using intensive grazing that moves around essentially trying to emulate the processes of, if you think about what happened on the buffalo prairie in the native grasslands. When the buffalo grazed it, they'd go in a big herd, they'd intensively graze an area and then move on. If you look at the grasses that grew in the native grasses that grew in those areas, they had incredible root systems. Most of their biomass was underground because the part that they would stick up above ground would get mowed off every now and then. But with a really big root mass, they were able to regrow fairly readily when the buffalo moved on. And so there's been places where people have been using intensive grazing and the manure that comes from that as ways to both return organic matter to the soil and also to return and enhance the microbial life in the soil. So I've been looking into and talking to farmers who have been bringing livestock back onto their land. And I think I'm hoping that sort of 200 years out, we're going to have reintegrated livestock production and crop production as two pieces of closing the loop in terms of nutrient cycling. I think that one of the big mistakes of modern agriculture has been moving animals off the land, isolating them in places where what they produce, which is essentially a very nutrient-rich resource, has been turned into true waste, and that's a waste.
Yes, again, thank you.
Thank you.
Two questions. One is, what's your comments on sort of the deep aeration of soil, topsoil, such as I think the French intensive methods? Are there any techniques for more progress made in planting in particular ways? And then the second question is, I know Paul Stamets, for instance, with fungi.com, has used mushrooms significantly in, for instance, oil spills, where there's been a real rapid increase of the fertility of the soils. Can that speed up topsoil?
Yeah, one of the, if you look at the role of fungi and mycorrhizal fungi in particular in terms of plant nutrition and bringing stuff to plants, the idea of inoculating soils with beneficial fungi or encouraging them, I think, is a big one in terms of boosting productivity and yields. In terms of using fungi to actually clean up things like oil, I don't know that much about that. I've seen a few studies on things like that. What I've been really impressed by in looking into the microbial world in general is how there's a microbe that can digest almost any natural compound. And so there's something out there that will eat almost anything, and getting the right things involved would do it. I was very impressed. I've seen some very impressive work where people find the right microbe to basically clean something up. There was an example. I gave a talk once in Vancouver, BC, where it was a TED thing where there was the people who were talking. A few people in front of me were a pair of schoolgirls from British Columbia who, as part of their, I think it was a middle school project, had essentially bred microbes that consumed phthalates, sort of a chemical that polluted areas around the Fraser River outside near Vancouver. And if I'm recalling what they did right, is they basically isolated a set of soil microbes, fed them only phthalates, and so they basically starved off everything else, and things that could eat phthalates prospered, and they went through that through multiple generations, taking advantage of the short generation time of microbes, till they they cultured a whole bunch of phthalate-consuming microbes, and they then released them into a very polluted industrial area, and those things ate and degraded the chemicals that were essentially behind the problem there. It was an amazing study. It made me feel completely inadequate that they'd done this as their middle school project. But it impressed me with the ability, not just with the cleverness of them, but also with the potential for trying to find the right microbes for those kinds of jobs. I mean, obviously the better solution is not to spill stuff like that in the first place, but in terms of cleaning it up, I think the microbial world, and whether fungi or bacteria, could really be allies for us. And I've forgotten the other part of your question, if there was one.
Oh, it was just about, are there any techniques like the French intensive system, apparently from a number of years ago, where there's more aeration in the lower parts of the topsoil that increases yield? Is there anything like that, or any techniques?
I'm not so much aware of that. Most of the work that I've looked at in the last few years is looking at minimizing disturbance of the surface rather than trying to open it up. And the idea is that it's soil life itself that will be creating the worm burrows and the arthropod burrows that allow air and elements to circulate, air to circulate freely in the soil. So I think the strategy that I've been seeing is the kind of like, don't mess with soil life, let them do their thing and foster them, and disturbance does not do that.
Great, thank you.
Thank you, David. I'm glad that you and your wife wanted to redo your front yard. I believe that we're in the Morpheus Neo stage, that we need to try to help people understand that there's different mindsets. I'm surrounded by conventional farmers, and I talk to them, and their main mindset is bushels, bushels, bushels. They are concerned a little bit about nutrition,
Right.
but not much. Where I, on the other hand, am concerned about nutrition, and as you have proved and others proved, the more you're concerned about nutrition, the yield comes automatically. So there's a couple, if you want to learn more about organic biodynamic farming, Rodale Institute and Acres USA are both very excellent. You can
Yep.
Google them and learn more about it. And I'm going to try to get David so he can speak at the Acres USA conferences here in the future. So
Yeah,
thank
I'm
you very
actually
much.
going to Rodale in June to look at what they're doing. Yeah. Oh yeah, the other one that's up there, The Rocks Don't Lie, that's my most recent book. It's a history of science and religion viewed through the way that geologists have studied and looked into the question of Noah's flood. What was it? And the way that theologians responded to the discovery that there was no global flood. So therefore, what was Noah's flood? It's a very interesting and rich back and forth in terms of, you look at the earliest geologists, or what we might call the earliest geologists. They didn't call themselves that yet, but back in the 17th and 18th century, they were all trying to figure out how Noah's flood worked. They were looking for evidence of that in the rocks. And over the course, I'll give you the two-sentence executive summary. Over the course of the 17 and 1800s, geologists pretty much established that there was no global flood, that it was not responsible for all the world's sedimentary rocks. Before Darwin ever got on board the Beagle, this was settled science. But the question was then, well, what was Noah's flood? Then there's two geologically plausible events for explaining Noah's flood as a regional flood that would have wiped out the world known to people in Mesopotamia. And so I go through the discovery of those discoveries and the theological arguments that then led to the very recent rise of young earth creationism, which, contrary to what most of its proponents argue, is actually one of the most recently developed branches of Christian theology.
Hi, thank you. Can you comment on massive composting and re-nourishment of soil as a possibility? I bring to your attention a town in New Zealand I know well, which is called Cromwell, which has a zero waste policy. And everyone is required, and this is a huge stone fruit community and a farming community, sheep farming community. Everyone is required to bring all of their organic waste to a worm farm, which produces a huge amount of organic recasting, recomposting, and then that goes back into the soil. And so the only things they have to get rid of are like refrigerators and
cars.
Cars, yeah, exactly.
I was not aware of Cromwell, but that's a very interesting example. The city of Seattle, for example, now has urban composting. So we've got a bin that the city drops off and takes along with we have a recycling bin, we have the garbage bin, and we have the compost bin. And this is, I think it's only been going for a couple years. They take it to a municipal facility, and they don't give it back to you, but they'll sell it back to you. But I think that idea of basically taking our organic waste and turning it into an organic resource is actually a really good one, and composting is a way to do it. Sort of large-scale aerobic composting can break down a lot of the nasties that are in urban stuff. The antibiotics, the pharmaceuticals, a lot of those things will get broken down if composted correctly. And the return of that organic matter back to agricultural fields is something that, it's safe to predict things for 200 years out, right? Because hopefully no one will be watching this in 200 years. and because usually, whatever anybody says for 200 years now, it's going to be wrong, right? But in detail. But I think in the broad sense, the idea that we're going to need to learn how to return nutrients that are in our organic waste back to the land at a large scale, that's an argument that's going to have long-term viability, because it makes sense in terms of closing the nutrient loop. If we're really going to get to a sustainable agriculture, we can't continue bleeding phosphorus into the oceans. So I think that the model that you're talking about in Cromwell, I'm not going to comment on sort of how it's set up or how it's run, because I don't know that much about it, and there's lots of ways that one could conceivably do that, but the basic idea underlying it, I think, is a really good one. Great. Well, why don't we stop it there? I'll be glad to entertain any other questions out in the other room, should people want to discuss further. I obviously recommend, Dirt, The Rocks Don't Lie, The Hidden Half of Nature. I recommend them all to you, but I am completely biased. Thank you.